No, for real, how does anyone know what time it is? Where does that, sense of time come from? And how is it that you always seem to get tired at, the exact same moment post-sunset every day? Incredibly, this is something that happens at the cell level. Our good Earth has had roughly the same day-night cycle for the entire time life has been here, just with the day getting slightly longer over time. So there's been some consistent evolutionary pressure for critters to find a way to keep track of a rough day-night cycle. You in particular have got a pretty complex network of clock proteins and cellular signals that all add up to establishing your wake-rest cycle. You might know this as your circadian rhythm. Anyone who's ever had to work a night shift or stumbled out of a predictable circadian rhythm can tell you that it is complicated to manage. Your day-night cycle relies on a whole bunch of different feedback loops. Mapping out the molecular foundations of your particular circadian rhythm can get really complicated in a deeply unfun way, especially in a quick video like this. Luckily, for every try-hard, overcomplicated mechanism in people and other eukaryotes, there's usually a much simpler analog in bacteria that can serve as a more palatable intro to the concept. And for the last 20 years, scientists have been studying the astoundingly simple molecular clock in a common freshwater cyanobacteria. This protein, called KaiC, works with a few other cellular mechanisms to maintain a near-perfect 24-hour clock day after day, regardless of what season it is. Unpacking how KaiC does this is a great way to learn about one of the most important fundamental reactions in biochemistry. More importantly, KaiC deploys a borderline physical magic trick to ensure it moves slow enough to keep track of the day-night cycle with almost no errors, which is practically a miracle if you understand how fast things move at both the cellular and molecular level. And I mean, come on folks, this channel's called Clockwork. It is honestly amazing it took us this long to cover circadian clock proteins. Let's get into it. And hey, welcome back to Clockwork. This channel is all about exploring the molecular foundations of life in a way that helps you build a deeper understanding of your inner complexity and how something as incredible as your mind can emerge out of the physical and chemical laws that govern the whole universe. In particular, this exploration of circadian clock proteins is technically a continuation of our series on senses, but it's kind of a stretch to call your circadian rhythm a time sense. Either way, subscribe so you don't miss a single episode, and check out our newly revamped Patreon to see how you can keep the channel going. But let's get into the meat of the video. Where are we even going to find these simple molecular clocks? You know what? They're gonna be right here. Meet the hero of our story, Synechococcus Elongatus, a freshwater cyanobacteria that grows really well in lab conditions, making it one of the most well-studied living things on the planet. These are the plants of the microbial world and the foundational building block of the food web, basically everywhere. S. elongatus and their ancestors are the primary producers of oxygen, so you can take a quick breath and thank this little guy for hand-stitching the breathable part of the atmosphere for you, one water molecule at a time. But the main thing we're focused on is that as a critter that survives by eating sunlight, S. elongatus really needs to keep track of time to better sync up with Earth's day-night cycle. If you're like me, you might be thinking a step ahead here and asking, why does this guy even need a clock? Can't they just turn on photosynthesis when they detect light? And I hear you, but we're going to answer that question once we see how this clock works. Stick with me, we're going to do this in the right order. If we dive deep into the cytoplasm of this bacteria, we'll quickly find the subject of today's video. Meet the world's simplest circadian clock protein, KaiC. Working together with its partners KaiA and KaiB, this protein keeps an incredibly consistent 24-hour clock using nothing but chemistry alone. Now, I want to start off a little technical here. KaiC is a chemical oscillator. If you crack open any analog clock, you'll find an oscillator at the core of the mechanism that allows it to tell time. An oscillator is simply anything that changes between at least two different states at a regular time interval, like a spring rotating back and forth inside this watch, or a pendulum in a more old-school clock, or the balanced motion of this metronome. Oscillators move in roughly the same way across a precise time interval. As a protein-based oscillator, KaiC tracks the time by changing its shape a few different times across a 24-hour period, with roughly the same shape changes happening at the same time every day. And this is critical. We'll get into why that's important later, but don't forget one of the most fundamental laws of molecular biology. Structure equals function. The shape of KaiC determines what it's going to be doing at a given time. Now, since KaiC is an oscillator, we're going to run through this cycle 3 different times at 3 different layers of complexity, so we don't get hit with too much information at once. I honestly think you'll have an easier time digesting it this way. Let's not waste any daylight and jump right into round 1. Let's see how KaiC and all its accessory proteins fit together at first. To start off, at hour 0, the very beginning of the cycle, a regulatory protein called KaiA will bind to the bottom of KaiC and kickstart the oscillator. And this is going to start a series of slow clock reactions in the core ring of KaiC's proteins. For right now, I just want you to imagine that KaiC is slowly tightening all day. And incredibly, KaiC's internal clock reactions have it approaching maximum tightness at round about 12 hours after this cycle starts. In fact, KaiC is tight enough at the 12-hour mark that it actually boots KaiA from the complex, and it's going to change its shape enough to allow our third character, KaiB, to bind to this part of the KaiC clock. KaiB basically helps deactivate the tightening process here. Now, KaiB is going to help KaiC start loosening back towards its start state. At the same time, KaiB is also the perfect shape to grab onto KaiA and sequester it, preventing this fella from accidentally restarting the party too early. But sure enough, KaiC will loosen up enough to kick KaiB and friends off the complex roughly 24 hours after this reaction began, allowing us to start all over. Cool, right? At the simplest level, KaiA is going to wind KaiC up, while KaiB helps wind the clock protein down. Simple enough. But those timings are not precise. You're going to see why at round about level 3. Stick with me here. Before we do that, though, what exactly are these clock reactions I was alluding to? It's time to get to the next level, y'all. And trust me, the biochemistry at this level is where the real meat of this video is. But let's explore that after we hear from today's sponsor, which is, plot twist, me. Today's episode is brought to you by our supporters over at patreon.com/clockworkshow. It's been a year since I relaunched this channel, and we've made a lot of progress, and we're now on the cusp of some really exciting new paths for the channel. So I'm relaunching our Patreon with a bunch of new tiers and actual rewards to make it the central hub for developing this channel moving forward. We are now going to finally have physical rewards, like a monthly handmade sticker club and 2.5D molecular papercraft prints, along with classics like a soon-to-be-launched monthly livestream and early access to a soon-to-be-launched second channel. Now, I've got a bonus video over at patreon.com/clockworkshow that anyone can watch. That video is going to explain our new tiers, and it lays out a roadmap for how we'll grow this channel over the next year. If you've liked these animations, now is the moment I would really appreciate your support so we can kick this thing into overdrive. Check out patreon.com/clockworkshow to learn more. But okay, enough business. Let's get back to the biochemistry. We're about to dive into level 2 of what makes KaiC tick, so let's tackle some chemical fundamentals. And you know what? Let's zero in on just KaiC for this run-through. All of those little clock reactions I mentioned earlier rely on one of the most fundamental and ubiquitous reactions in biochemistry. That's right, folks, we're talking about phosphorylation, or how your cells move energy around to keep things moving at all times. And okay, let's do a warp speed overview of phosphorylation before the less hardcore biochem folks get bored and bail. All living things consume food to get the energy they need to stay alive. In our mitochondria, and in the membranes of bacteria like S. elongatus, a turbine called ATP synthase transforms food energy into this universal catalytic currency, adenosine triphosphate. And for simplicity's sake, ATP moves energy around your cells by popping off this last phosphate group at the end, turning it back into adenosine diphosphate. And one of the ways this is actually an energy transfer is that rogue phosphate group can get stuck onto a protein, forcing it to change its shape enough to change how it works or exactly who it binds with or whatever. So sure enough, getting a shiny new phosphate group attached to a protein is called phosphorylation, and this is a wildly common event that happens in cells, since ATP is constantly getting produced and distributed throughout basically all cells. For the most part, there's this ubiquitous massive family of protein workers called kinases that wander around and use ATP to phosphorylate their partner proteins. But KaiC is incredibly cool because it phosphorylates itself. It does something called autophosphorylation. Which is a word that sounds way weirder out loud than I thought it would. But yeah, now it's time to adjust our language from level 1. Instead of KaiC tightening and loosening, it's phosphorylating and dephosphorylating itself. Let's check out precisely how. KaiC has this perfect little pocket down here where ATP can bind. This is the C2 domain of one subunit of KaiC, and usually the ATP spot here is covered up and inaccessible. KaiA binding is going to uncover the phosphorylation site, which is going to kick off this whole process. And the process here is simple enough. This domain has 2 slots that can get phosphorylated, so for the first half of this clock cycle, 2 ATP molecules are going to show up and donate phosphate groups in this order, until these ATP slots are full. Each time one of these phosphorylations happens, KaiC's shape changes a little. Once we hit maximum phosphorylation, KaiC's shape will change enough to boot KaiA from the complex and allow KaiB to bind. With KaiA gone, these phosphorylation slots are covered up once again. And this is where we get to discover one of KaiC's superpowers, because it can actually remove these phosphate groups by itself. It's able to reverse its own phosphorylation. I need to really hammer this home, y'all. Usually, this takes two separate proteins, a kinase to add a phosphate group, and a separate protein worker called a phosphatase to catalyze the release of that phosphate and deactivate the main protein. Instead, KaiC's active site down here is so dynamic and shaped so, well, ambiguously that it can do both jobs depending on if it's Kai-A or Kai-B bound to the complex. So the loosening process here is just KaiC gradually booting these phosphate groups off. But getting back to the actual reactions, once KaiC is fully phosphorylated, fully tightened, Kai-B will bind and inhibit phosphorylation. KaiC then spends the second half of the cycle pushing these phosphate groups out of the C2 domain. Sure enough, booting both of these phosphate groups from KaiC will take roughly 12 hours. And to be real with you, the precise timing here is pretty complex and depends on a lot of factors that just don't really make for decent YouTube material, and trust me, I tried way too hard to make it work. So please, let's just put a lot of emphasis on the word roughly there and understand it's kind of a hazy range, actually. And remember, Kai-B holds on to Kai-A after it binds to the complex, so that's going to guarantee that those phosphate slots will stay closed for the entire second half of this cycle. Unless KaiC is actively being phosphorylated, it's actively working to push those phosphate groups off. Nice. But that's it. Level 2 is basically KaiC transitioning sequentially between 4 states. Let's rotate to a top-down view so you can see this happening with all 6 of KaiC's subunits. Once Kai-A binds, KaiC will gradually add one phosphate, then a second one across 12 hours. Kai-B will then slam the door on the phosphorylation party, allowing KaiC to gradually boot these phosphates and return to normal. And I love that we can simplify the mechanism this way, but if you're me, it's a little unsatisfying, because it is honestly wild that KaiC somehow only shifts between 4 states across 24 hours. Because phosphorylation usually isn't even close to this slow. Like, if you've watched my video on DNA transcription, you know that RNA polymerase II can get phosphorylated dozens of times over the course of a single second's worth of RNA production. How on earth are we going to slow down biochemistry enough to track actual daylight? Is this clock protein, like, tightening in billions of really small steps? Or is there something here way cooler than that? Are y'all ready to put this together and see how the full clock works? With just a little more chemistry, we can lock in a full explanation here and put this all together. Welcome to Level 3, the deep biochemistry. Now, before we rotate through the next cycle, let's take a longer look at KaiC real quick. This protein is a hexamer, which means it's built out of 6 identical subunits all connected together like this. But rotating it back to our original view, look, each subunit actually has 2 distinct biochemical domains. We've pretty much ignored the top half of KaiC until now. All of that important phosphorylation happens in the bottom half of KaiC, the C2 domain of the protein. But the timing of those reactions is governed by the top half here, the C1 domain. Now, C1 also binds to ATP, but it doesn't phosphorylate itself. Instead, C1 is an ATPase domain. It does something called ATP hydrolysis. It just grabs some energy from splitting ATP to push the rest of KaiC across a difficult transition. And again, how C1 does this is pretty hazy, but one proposed mechanism goes like this. KaiC's C2 domain needs to be flexible in order for these phosphorylation reactions to happen. And KaiC gradually becomes more flexible over time. But then, C1 fires off an ATP hydrolysis, and that burst of energy shocks the whole complex into being more rigid. In short, occasional bursts from C1 block C2 from doing its job, slowing the whole complex down so it can operate on this 24-hour timescale. And therefore, C1's little energy bursts become the quote-unquote ticking that sets the pace of this clock protein. Nice. Teams working on KaiC have done an incredible job establishing that breaking ATP up in this C1 domain governs the pace of S. elongatus' circadian rhythm. But the precise how is still a little unclear. Either way, covering the basics, in normal cell conditions, C1 will snap off some ATP energy just shy of 16 times a day, like on average 15.8 times a day. And this pace is shockingly stable. There's certain circumstances where C1 will go faster or slower, but it averages out to consuming 15.8 ATP molecules per day. Mess with the C1 domain and KaiC's phosphorylation cycle will go all out of whack. But the truly incredible thing about C1, and the part that really matters for the scope of this video, is that it's able to maintain such an incredibly slow rate of ATP hydrolysis. A similar complex, RUVB, hydrolyzes ATP around 8,000 times a day. So KaiC isn't even in the same galaxy as proteins in its class. And that begs the question, how on earth is it able to do things so slowly? And the answer is simple. It's built in a way that it's kind of bad at its job. Let's finally get to the deep biochem and see how ATP binds to this weird little complex. Normally, when ATP is in a binding site like this, it immediately gets catalyzed to break off its last phosphate group. But this is the magic of KaiC. This is why you stuck it out to this level of the video. This C1 domain of KaiC is an annoyingly weak binding site for ATP. ATP enters the C1 domain just fine, but this little binding pocket just isn't perfectly set up to catalyze the hydrolysis of this reaction. So the ATP is just going to be stuck here doing nothing. And okay, I want to unpack that with the most technical 45 seconds of this entire video. I hate organic chemistry way more than you do, so let's blitz this segment before my brain actually melts. And again, if we go all the way into C1's binding pocket, there's two main chemical reasons why this catalytic center is so bad at breaking ATP. First up, the little pocket here that's supposed to pull off the phosphate and attach it to itself is just like a little too big and charged in just the wrong way, meaning that this binding pocket will hold onto a water molecule just a few angstroms away from where it needs to be. Remember, this is all chemistry at the end of the day, and that means we need actual chemical reactions to happen. ATP hydrolysis isn't magic. In order to break this phosphate off here, we need a water molecule to do the actual pulling, right? And that's not a technical term. Water can't get into the right place in C1's active site, so our ATP will just kind of hang out here in the binding pocket. And then, in order to push the binding pocket into a better position for ATP hydrolysis, this little section of the active site needs to do a pretty huge transition. It doesn't look like much, but this movement is very energy unfavorable, meaning C1 will only stumble into the exact right position a handful of times a day. At this level, there are a few extra little biochemical details we can get lost in. For example, the more phosphorylated KaiC gets, the less flexible and more rigid some of its subunits become. So I wasn't completely off base describing phosphorylation as quote-unquote tightness in level 1, but that metaphor can become real unhelpful real quick. I only bring this up because once KaiC hits maximum phosphorylation, that rigidity is what exposes the binding site on the top of the clock complex where KaiB can attach and arrest the phosphorylation reactions. And this final part is probably one of the haziest transitions. At the end of the cycle, the KaiC complex is so rigid that it becomes a terrible place for KaiB to bind, which gradually pushes KaiB off the complex, allowing the cycle to reset. But, don't hold me to that description. There's a lot more science to be done to fully explain a few of these transitions, and we've probably already gone a little too deep into the biochem here, so let's start putting a bow on this by powering through one final full mechanism explanation. KaiC's C1 domain is constantly, gradually hydrolyzing ATP at roundabout every 90 minutes on average, ensuring that things don't move too slow. In the morning, Kai-A will kick off the cycle by binding to KaiC and opening its phosphorylation slots for business. KaiC will then spend roughly the next 8 hours trying to fill 2 phosphate slots in its bottom C2 domain, while C1 shakes things up and prevents it from happening too fast. Once KaiC is fully phosphorylated, it will gradually push Kai-A off the complex, leaving the door wide open for Kai-B to bind and start inhibiting phosphorylation. If KaiC isn't actively adding phosphates, then sure enough, it's actively removing them. It will take approximately another 8 hours to fully dephosphorylate KaiC, at which time Kai-B is going to get the boot, which brings us back to the starting state so the whole thing can start over. Awesome. Kind of a mouthful, honestly. And while that's cool, one last thing. What does this cyanobacteria, do with this information? And you know what? Let's try to wrap this one up. Life is all about energy efficiency. We need to take in as much energy as possible while minimizing how much energy we spend to get it. A clock protein like KaiC is a great way to start transitioning between day and night modes without relying on something reactive like overall light levels. Quick review here. Photosynthesis comes in 2, honestly, very labor-intensive steps. First, you've got to harvest all this light energy, and then you have to do the work of storing that solar power as something chemically useful. First of all, it takes a ton of energy to build photosynthetic antennas, and those things are so wild and dynamic at their biochemical level that you can't just leave these proteins lying around all night. They'll honestly explode. We have to pack up these proteins and dump energy into the dark reactions and the Calvin cycle. And it's a lot better if we can predict when this is about to happen, as opposed to either wasting a bunch of daylight or a bunch of nighttime. in the transition. So, in order to actually guess when this happens, when KaiC hits maximum phosphorylation, it's just the right shape to activate a messenger protein down here called SOS-A, which is then going to pass that activation onto a master transcription regulator called RPAA. Now active RPAA proteins are going to bind to about 130 different genes in S. elongatus' DNA, leading to their expression. It turns on these genes. All these genes add up to the day-night switch between photosynthetic harvesting and Calvin cycle storage. RPAA also helps determine when S. elongatus can divide. This cyanobacteria will take advantage of all the extra energy it's storing at night to lengthen, but it's not going to divide until the morning, when both daughter cells have the maximum amount of time necessary to harvest light energy so that the next generation has the maximum chance of being successful. KaiC also helps signal chromatin expansion versus condensation in these genes, making it more likely that they'll be transcribed. And KaiC typically reaches full phosphorylation in the late afternoon or early evening, making SOS-A kind of a dusk signal that helps S. elongatus pack things up for the night. And once KaiB binds, that protein is the perfect shape to activate another worker, CIKA, or SIKA, which literally is there just to deactivate RPAA. Now this is what makes a slow, floppy oscillator like KaiC so valuable, because SOS-A starts binding to KaiC as soon as it gets more and more phosphorylated, right up until it gets outcompeted for its binding spot by KaiB. This ramp-up typically leads to a 4-hour period just before dusk where RPAA is getting strongly activated. Rather than a rigid system, this ramp-up allows for a short, specific transition to night mode. We're just beginning to unpack how KaiC helps S. elongatus adapt to changing conditions. If you want a kind of follow-up to this video, I hope you'll check out the article from Asimov Press that pushed me to make this video in the first place. I mean, there isn't a single week I don't find something I want to steal from them or their editorial lead, Nico McCarty. Asimov is doing incredible work making the industry and cutting-edge side of this new revolution in the life sciences accessible and super exciting. I only wish I had a little more time outside of developing this channel so I could actually pitch them a few articles. But whatever. Read their article about how a small team figured out that S. elongatus can actually adapt and gear up for seasonal changes, not just daily cycles. Give these folks 5 clocks out of 5 and call this the mini Clockwork Book Club entry for this video, and let's move on. Anyway, with those hazy boundaries in mind, let's go ahead and put a bow on this video. The main thing I want you to take away from this channel is a sense of how malleable life is. When folks talk about cellular processes, things can come across as deeply mechanical. A rigid input yields a rigid output. You can feel kind of boxed in when you start to learn about things like the central dogma. But life is incredibly flexible at its fundamental molecular level. Things are very much not mechanical. And even though it's the literal name I picked for this channel, the inner workings of a cell are very much not clockwork. Instead, the more you learn, and hopefully the longer you stick with this channel, the more you're going to see an intricately balanced network of imprecise feedback loops. This wiggly, fuzzy nature of biochemistry can yield rigid results, like, you know, how a floppy clock protein can gradually soak up cellular energy in a way that allows it to tighten precisely on a 24-hour timescale. However, it's that fuzziness that's given us strength for our whole history. The messy, compromising nature of biochemistry gives rise to evolution and a gradual staircase towards complexity. Your malleability is what really makes it so you can survive and thrive in this ever more complicated world. Never forget that we are ultimately the complex consequences of shockingly simple and sometimes bendable rules. In the end, life just works. The more you leave living systems to work, the more they're going to surprise you. For now, though, we don't need to let this clock run any further. That's a pretty good place to leave it. I really do appreciate your time. Thank you so much for being here. And as always, thank you so much for sticking with us to the end of the video. If you like this video, it would mean a lot to me if you subscribe to this channel. And also, if you made it this far, I'd love to know what your favorite species of cyanobacteria is. It's actually really important information for me. At the same time, it would genuinely mean a lot to me if you checked out our State of the Channel update over at Patreon. I'm really excited to keep building this with y'all and to see just how far we can take this thing. Check us out over at patreon.com/clockworkshow. Otherwise, you can always check us out over at watchclockwork.com and sign up for our newsletter. That's something that will always help the channel in a way that is higher impact than you might realize. But for now, it's a pretty solid place to end this. And so as always, I just like to leave you with peace, love, and full phosphorylation. Everyone be well. Thank you so much.